So we have three speakers today on this panel. I'll introduce them in the order in which they'll speak. Bill Close, to my left, is with Wendt Corporation. Wendt Corporation is very respected in its field of non-ferrous systems and shredding plants. And Bill has been with Wendt Corporation for 28 years. Bill has a Bachelor's of Science degree in Industrial Engineering and Computer Science. He's had a variety of roles at Wendt Corporation over the past 28 years. His career has spanned fields like non-ferrous technology developments ranging from Z-Box, concentrators of ASR, wet recovery systems, and eddy current systems, to name a few. For the past 16 years, Bill has led Wendt's process and technology efforts developing non-ferrous recovery and sorting systems of ASR, with a strong focus on the proper application of sensory sorting, which is the subject du jour. His travels have included worldwide investigations of commercially viable technologies, and he has spoken overseas, for example, at the 2008 Conference on Sensory Sorting in Aachen, Germany, on XRT, sorting of Zorba. Following Bill, Philippe Bloit will be speaking today. Philippe was born in Old Orleans, not New Orleans. He hails from France, a graduate of École Nationale Supérieure de Géologie. Not really. It's the best I can do with my French, in Nancy, France. He's lived most of his life, more of his life he's lived on this side of the Atlantic, mostly in Salt Lake City, since 1989. His career began with metals and minerals, but they were the virgin type, working in mining, mineral processing, developing computer modeling techniques for analysis and optimization of design processes, and flow sheets for iron ore, base metals, and precious metals, as well as industrial minerals and fertilizers. In a more recent time, since 2013, Philip has taken up interest in recycled metals and has been working with the newly formed company EDX. Following Philip will be Dr. Nailan Kumar. Nailan is the founder and president of UHV Technologies, which has operations in Lexington, Kentucky, and Fort Worth, Texas. Nailan received his PhD in electrical engineering from Drexel University in Philadelphia. He's an expert in nano materials, devices, and applications. He has 62 U.S. patents in these areas. In particular, he has extensive experience in X-ray technologies and instruments. Over the past 30 years, Nailan has received over $20 million in R&D grants for developing new and innovative technologies, and these have been spun off into several companies to commercialize the technologies. Of more recent time, he has been working on the development of X-ray fluorescence sorters, sensory sorters for metal alloys. And in the last 4 years, he's been receiving funding from the U.S. Department of Energy ISRI activity. And that's our esteemed speaking list. So I'm going to now turn it over and let the gentlemen speak about their subjects. And at the end, we'll have a Q&A. So please jot down your questions so they don't slip your mind later. Okay? Bill?
Good afternoon. All right. Well, let's talk about sensor sorting. What is sensor sorting? Well, it's typically a fast-moving conveyor belt with a sensor mounted either above or below the belt, and a method of ejection of the material. Commonly, this would be electronic valves that have bursts of compressed air to eject the material. The various sensors are wide-ranging, could include electromagnetic, which is a metal detection sensor, XRF, X-ray fluorescence, XRT, X-ray transmission, which would be a clear-through read of the material for atomic density, color, and a variety of other. Various applications would include municipal solid waste, plastics recycling, electronic scrap, auto shredding, packaging, paper, and there are other applications. Today we'll just focus on one of those topics, auto shredding, and we'll begin with metal recovery as the application. This is a flow diagram of a sensor plant that we've put up in Medford, New York. This is a companion plant that would be working alongside the traditional eddy current plant where you're recovering your Zorba. And this would be working on the post-eddy current drop. Begins at the beginning here with a batch feeder, continues through air classification, and then sensor sorters. This is a video of how the technology is working. Again, this is metal detection only. The sensor coils are located underneath the conveyor belt. Particles are nicely singulated by the speed of the belt. In that first process step, we were looking for an all-metal recovery. And then the all-metal recovery was then presented to the second machine where, again, it's metal sensors, but here we're targeting specifically the insulated copper wire to shoot that out of the stream. So here's the example of the materials that have been recovered after the eddy current, where we're now pulling out insulated wire and bare wire concentrate. The remainder, after we've extracted the wire, is presented to the last step here, where here we're going after mixed non-ferrous metals, a Zurich fraction. You have to pardon my iPhone as I'm kind of walking around here. And here's the example of the Zurich fraction coming off. This is commonly used technology, widely implemented in our industry today, and I would bet most of you are doing something similar to this in your own yards. Kind of going a bit further and looking at other applications. If we pick up the Zorba material that was coming off of the eddy current, there's an opportunity to derive extra value from the mixed aluminum and heavy metal fraction, which is called Zorba. And once again, through sensor-based sorting, we're able to extract the value from the stream. Example here being with X-ray, we're able to determine a classification of the metals. We have light images and dark images. The light typically would be the aluminum, but we could also have some light images in the X-ray that would be plastics. Same brightness, but different atomic density, and we can actually tell the difference and place them in the right column. And sorry about that. Didn't know there was volume on this thing. There we go. I'll just get that turned off there. Yep. Sorry about that. We'll just go forward. But unfortunately, I've got music on some of these others, so I was just assuming this to be silenced. Give me one moment. Yeah. All right. We'll have to deal with the music. Here's an example of Zorba sorting. This is at the Went test facilities in Buffalo, New York. So we have our commingled aluminum with heavy metals fraction that's being input into the X-ray sorting. Here we're separating the material by atomic density. And we're ejecting the heavy metals from the fraction here. The drop then will contain the aluminum as well as the light waste. The remaining aluminum with light waste we're then putting over an eddy current for the process of removing the trash content and then producing a twitch fraction. So the goal here is, this is an alternative to a heavy media operation where we can actually produce a clean twitch fraction of quite high purity. Now returning back over to the X-ray machine that had ejected the heavy metals, we have another option where we can put a color sorting unit. And here we can extract additional value from the mixed heavy metals. In this particular example, we're targeting for red metals, wire shapes, and circuit board, and then creating a high value fraction. And then the remainder is going to be a zinc package. And apologies for the music there. The color fraction can be further separated with additional passes where we can segregate into yellow brass and copper. And we have the ability also with the fines sorting unit, the Combi-Sense chute, to go further into the fines fraction and do similar sorting steps. Back to the product that was produced from the X-ray unit, the Twitch, we could actually go further with that with the same XRT process with a wrought cast program. And now we got equipment noise. So here with the X-ray equipment, now we're measuring the difference in aluminum between a higher alloy and a lower alloy material, and producing a wrought product on this side of the equation here. And then on the other side of the equation here, we have the cast coming off. This is XRT. It's the same XRT that was used for originally beginning with the Zorba, where we then segregated the twitch from the heavy metals. We're just picking up the twitch, reprocessing with the same machine, different program. Similar ideas in that you're looking for targeting the heavy metals, but now it's the heavy metals are inherent in the aluminum itself. So your higher alloy, such as zinc, is the target that you're shooting for. This particular example, we pre-screen the material to take out the 3/4 minus, and then created a separation of the greater than 3/4. An example of chemistries coming off that, the pre-screened material, it was twitch at the beginning, it was screened at 3/4 minus, and the melt analysis on that would be very similar to a 380 alloy without further processing. By removing the 3/4 minus, we're able to significantly increase the throughput. It's roughly double the throughput without having the fines present, and the chemistries are acceptable. Another common example for the same core technology, XRT, but different feedstock, would be more of a quality control application. Examples could be tantaber or extruded aluminum, such as window frames, where there the quality of the scrap is already very good, and you're just looking for contamination removal. Other commonly available technologies out there include XRF, and I figured I'd put up an example of XRT and XRF side by side so we could have a look at that. XRT, basically we're taking the energy of the X-ray clear through the particle, and we have a measurement below the conveyor belt, so we're measuring the differences in absorption of the energy as it passes through. Whereas XRF, you're looking at the reflected energy and doing a spectroscopic analysis. The XRF has a greater degree of detection ability, so you can see a lot more with that. But our experiences have been that it's roughly twice the cost of the XRT, lower throughput, and higher operating costs. The business case just doesn't seem to be holding up for XRF. New technology that we have available is LIBS. This is laser-induced breakdown spectroscopy. Purpose of this machine here would be to go beyond what was accomplished with the XRT. XRT will still be the backbone and the bulk sorting tool. But once you have concentrated your aluminum and would like to do alloy separation, LIBS is going to allow you to go beyond. There are two different methodologies of which LIBS is being implemented in the industry. One of them is the dynamic laser, and the other is a static laser, and I'll show you the differences. In the case of the static laser, you can see on the graphic here that you have a single file arrangement of the particles, so the materials are put through a product channel and then distributed. And I have a video of that running, thankfully without noise. And with a single file, you've got some limited throughput with the product, even though you have multiple channels that it can be done side by side. The dynamic laser is quite similar in the goals, but the laser is able to acquire targets widely spread across a conveyor belt. So the advantages here would be substantially increased throughput. So similar to the other sensor machines that you're familiar with, where you're working with a wide conveyor belt, widely distributed product here, again, you can have the particle randomized across the belt, acquire the target, and then shoot on that. What's being accomplished with either the static or the dynamic is when we're hitting it with a laser, you're creating a plasma burst, and then you're sampling that to identify the specific alloy. So this gives an opportunity, for example, to separate the 5,000 from the 6,000 alloys, or go even more precise within different alloy groups. So this is commercially available today. I don't have that information off the top of my head. So the next topic I have here is gamma systems. And these commonly have been applied in the industry on ferrous scrap for measuring the average copper content. This is an example of a post-process analysis that can be done. It allows a lot of precision for detection of the scrap and can produce certified loads. This technology is now being applied in aluminum applications and following, for example, XRT machines. Gamma's text model basically is they want to align their technology more with the consumers of the scrap. So this would be more of a secondary aluminum furnace that would be interested in knowing rather than guessing what it is that they're buying. And typically the contract would be with the secondary furnace, even though the equipment might reside at the processor. So this is kind of the next evolutionary step in the industry. So anyways, thank you for your time.
1 minute and 30 seconds over. That's pretty good.
Okay, well, we started it.
Really let you go on that.
Yeah.
That's fine. Really?
So
I don't start the clock until it comes up.
do I?
Yeah.
This one?
No.
No. Where's the magic? There we go.
That's another reason I
It's
invited
magic.
Bill.
Thank you very much. So I'm going to talk about an eddy current sorter and a new generation of eddy current sorters, even though there have been previous iterations based on this idea probably some 20 years ago. People have dabbled in that with limitations due to the technology available at the time. So first of all, this is a little bit different than the topic of this conference this afternoon, as we do not censor or measure anything in that system. We simply use properties of the elements and the particles to separate them. But we do not know if it's copper. We just know that it has this kind of conductivity and reacts this way to the process that we feel. So in that sense, we don't go in the two steps that Bill explained, where we have a sensor followed by an ejection system, a mechanical ejection system, usually an air jet. So we'll review first the standard eddy current technology. To generate an electric force in a particle with eddy currents, we need to generate an electromagnetic field, an alternating magnetic field. And we need to have those particles, the particles, pass through the magnetic field. The way this is done in the standard eddy current machines is there is a rotor underneath the conveyor belt that spins at a few thousand RPM and is lined with north and south magnets. This rotation speed generates a rotating and an alternating magnetic field. This system is limited, therefore, in frequency to the mechanical speed we can rotate the drums with. In practical terms, this means that the systems that we have, no matter what the vendor is, are limited into the 1 kilohertz range. What we looked at the University of Utah and now at EDX Magnetics, which is a spin-off from the University of Utah, is how can we generate a magnetic field using a non-moving system. So how can we do that in a steady state, or fixed system, non-moving parts? And the team at the University of Utah, that you see the people lifted there, got a grant from the Department of Energy 3 years ago. At the beginning of 2014, we started that project. And that was parts of the metals program at ARPA-E to try to devise methods that would be able to sort scrap on a variety of potential options. And that funding resulted in the development of a system that looks schematically like this. So we have a hopper, a conveyor that projects mechanically the particles into a gapped magnet. So the magnet that you see is actually horizontal this way in the system, or angled, but not in this angle. And the particles that are more conductive and less dense are receiving a higher force than the particles that are less conductive and denser. So we can separate, for example, aluminum from copper. We can separate brass from copper. We can separate a variety of metal particles, providing that they are consistent in size and different in conductivity and density. So the large advantage of this is the frequency that we can use, which is the one term in the force generated into the particles is the frequency, the other term is the field. That frequency we can run because we drive that magnet with electronics. We can generate frequencies up to 50 kilohertz. We have run mixes up to 50 kilohertz. Typically, the smaller and the finer the particles, the higher the frequency we need to run. On the system that we had at the show, we were running at 22 kilohertz to separate particles of brass from particles of copper that were in the 1 to 4 millimeter range. If we want to separate things that are more like angel hair copper particles, we would have to go to potentially 50 kilohertz or higher. The other advantage is there's no contact and no moving parts, so potentially a lot less maintenance on the system. And we can separate particles that are small, which the top pictures on the right. So we have a vibrating feeder feeding particles directly into a gap. We also looked at the time, two sort of almost perfect materials, because it was more of a proof of concept system. One was copper and aluminum up to about 1/2 inch in size, and we looked at different mixes and different sizes to determine which conditions we needed to run at. And the other was electronic scrap, with the idea there was to try to separate the capacitors that contain niobium from the rest of the components from a board. This was successful enough that we got funding for the following 2 years. The second year, we started looking in really two directions. One was looking at small particles, because from our contacts in the industry, we saw that a number of people were producing mixes and could add value to those mixes by separating them. And the other avenue was to move to larger sizes and Zorba. On the zebra type material, we experimented with a number of products, and the early prototype unit that you see there is the prototype that we showed at the ARPA-E Energy Summit in Washington, D.C. That's usually in February or early March. And so that was February 2016. And you see the two products there. And what we demonstrated at this show with our third generation prototype unit or demo unit was the same sort on the same material, because this material is produced by one of our contacts in the industry, and they would like to upgrade it for their customer to upgrade their value. So that's the feedstock, which is about 65% copper and 30% bronze or brass, and then 5% to 8% solders, stainless steel, other. It turns out that there's probably a little more than 5% stainless steel in the mix, but that was sort of the original idea. And the sort produces either a number 2 copper, so 98% plus copper, or very close to it, at 90% recovery, meaning that 90% of the copper that's in the feedstock ends up in the copper product. And the reject bin, which they call the drops, is all the less conductive material, so it has your brass, your stainless steel, and your solder materials, so precious metals as well as zinc, lead, tin type elements. On the fine Zorba side, we started with a copper aluminum mix, and we could upgrade we could produce an almost pure aluminum product, and a product, on the other hand, that wasn't pure copper but was significantly enriched in copper. In this case, the sort bin, the aluminum, is kicked more than the copper. So depending on how we tune the magnet in terms of power and frequency, we can change the sort from metal to metal or alloy to metal. The next generation that we're looking at in some ways is, instead of having a gapped system, have a system with a belt, and the magnets being either under or over the belt in a different configuration. And the first tests that we've been running are on pre-calibrated copper and aluminum plugs. And with material like this, as a proof of concept, we have run tests that give us basically a perfect sort. one particle of aluminum in the copper bin and one particle, one plug of copper in the aluminum bin. So this is promising as a concept, and says it's something that should be doable in a short while. This isn't yet a commercial product. We have also tested on a number of other fine materials. There's a lot of processors that have a variety of products, from fine Zurich to fine zebra to caps, titanium, aluminum, of different sorts. And that's the sort of another avenue of applications. So with a tunable magnet, we have the potential of doing that. We also, as both a research and a process design exercise, developed a complete model, finite element model of the system, including the trajectories of the particles, so that we can run simulations of a mix through the system to determine the optimal conditions to run it at. So we're focusing on fines with the current system. So the Zebra system is going to be our first sort of commercial applications. And that's the demo we had at the show, and that some of you at least saw working on the booth. Pricing-wise, we should be competitive with a standard eddy current. And capacity-wise, we have flexibility, depending on the electronics we use, to add magnets in parallel to run a system that's adapted to the customer requirements. So in summary, the benefits of this technology are that we can capture value from products that are currently stored in that are not standard commodity products. So we can make them into commodity products that are sold on a more open market rather than a handshake contract, person to person. We have the advantage of keeping this material in North America instead of shipping it to China to be sorted and then imported the parts back to America. And the only sort of comparable methods seem to be significantly more expensive. So in this area of small and fine elements, we seem to be very competitive, and we seem to have a place in the market. First time I've been on time in a long time.
Well, you were a minute and 15 seconds over.
Okay, very good.
You're the outlier.
All right.
Alan, you want to tell us?
Thank you. Close this. Yeah.
All right, thank you, Tim. So I will talk this afternoon about the high throughput X-ray sensors fusion metal scrap sorter we have developed with funding from DOE ARPA-E. This was, as Philip mentioned, part of the same program, the metals program, which really started in end of 2013, and we have just completed 3 years of the project, and it is continuing. And it's a joint development between Phoenix, OmniSource, IRIS, and UHV technologies, which is also known as nanorange. So let me just give you a little idea about X-ray fluorescence, XRF as it's commonly known. As you probably know, X-rays have been around for about 120 years, and everybody's gone through X-ray imaging, chest X-rays and CT imaging and all that stuff. And that is essentially X-ray transmission, where the X-rays pass through a body or a piece, and then you can measure the absorption, and as Bill described in detail, can be used for scrap sorting and is being used for scrap sorting. And X-ray fluorescence is the process where we, I don't think the cursor goes. Do we have a pointer? But anyway, the first figure on the left, or the right over there, is essentially where a primary X-rays, which are on the order of between 15 to 50 keV, and force a inner shell electron from the atoms, and a outer shell electron falls into that place. And since the people who understand the physics really know that the bands, the orbital bands are fixed. So by knowing when the outer electron falls into the inner shell, it emits a photon, which is in the X-ray energy range. And that is unique for every element. So by measuring those elements, or those X-rays, which are the fluorescent X-rays, which are we don't want to call them secondary X-rays, but the fluorescent X-rays, you can actually determine what the chemical composition of the material is. And you can measure those X-rays all the way from the whole periodic table, from lithium all the way to uranium. And it is a unique value of that. And in this figure, which is and you measure those fluorescent X-rays, and you can measure the energy and the number of X-rays, which are called the counts in the industry, and you can actually determine the exact chemical composition of a material. The technology has been known for more than 50 years, as I'll show. And there are two main methods to analyze the energy of the fluorescent X-rays. One is energy dispersive, commonly called as ED-XRF, and the other one is wavelength dispersive. And both of them have advantages and disadvantages, and they have been used extensively over the last, I guess since the 70s, for analytical instruments. And there are probably 250,000 units out in the field in every university and a majority of the companies which do any analysis work. So as I mentioned, XRF has been known for more than 50 years. It's a analytical instrument where there are companies like Rigaku, Bruker, Olympus, Niton, Thermo, and everybody have been selling units for a long time. And all of you who were here earlier this week have seen that at the show there were probably 6 or 7 companies selling XRF guns for about $20,000 to $25,000. And that can do all the aluminum alloys and every metal rocks and everything can be done. And they are very, very common. So the XRF technology has the capability, not only in the laboratory, but also in the field, in handheld units, to be used for analysis and identification of alloys. So where is the problem? The technical challenges. As the two previous speakers talked about the problems with XRF, cost, reliability. And when we started the project 3.5 years ago, that was the goal. How do we change the paradigm? Because the physics was very well known. The components and everything was very well known. Our challenge was, how do we change the paradigm where this technology, which is very well established, can be used for very high throughput, inline sorting of aluminum alloys, which at that time could not be done by any means. And we'll talk about that a little bit in the next few view graphs. I won't go through all the whole list of all the issues and everything, especially most of them are all the physics limits. So our goal was, how do we reduce the cost of capital equipment, which was, I won't really go into the details of different companies. And how do we reduce the sorting errors due to different shapes, content, and the quality of the scrap, and the painting, and the oil, and the dirt on those things. And another issue, which I'll show in the next slide, which everybody said, well, we want to measure 5,000, 6,000 alloys. You cannot really measure the low Z elements. Low Z in this case is a low atomic number, magnesium and aluminum, using XRF. But as you know, that we do that with the XRF guns every day. So the issue here is that the XRF gun we hold to the piece. In a high throughput system, the pieces are of variable size, different height, so we can't really touch the XRF unit to the piece, so we really have to really solve that. And the solution we basically have is a mixture of EDXRF and the WDXRF to have optimized X-ray sources and detectors. We have our own designs. We do simultaneous detection of more than 10 elements, and then we extensively use intelligent software with XRF and optical imaging. Our optical sensors are essentially capture three-dimensional images of every piece and give us much more information, just the color sorters and all these things. But let me just talk about the first issue, which is what everybody told us when we started, all the reviewers of our proposal as they go with the government grants. When a PhD proposes something, there are 10 other PhDs who say, no, it cannot be done. Okay, so the main reason for that is, if you look at the end of, this is the absorption of X-ray fluorescence energies for different elements through about 1/2 inch of air. And you can see for magnesium, it's 92% absorption and only 8% is passing through. Okay, while for zinc, it's 95, only 5% absorption. And that is different. So if you have a piece which is going through a 4-inch absorption gap, then you're not going to see most of the aluminum and magnesium. So the way we do that is that we have our hardware, which is very low noise levels, and then we account for the gap or the size of the pieces, and we account for that in the software, which allows us, and then we use artificial intelligence, neural nets, to really determine what the numbers are. The second thing is that when in a typical XRF gun, you capture about 30,000 counts. When we are doing this at high speed, we have 10 milliseconds for each piece. So we're getting only 100 or 200 counts. So again, the neural nets solve that problem. We have such a large amount of noise that we actually train our computer again and again and again for a particular signature, and we use that. So we can have hundreds or thousands of signatures in the computer and allow for all the errors. So this is the original slide from the ARPA-E when we started the project. And of course, the first sections are what the reason why Department of Energy was putting in several $1 million, or actually the whole metals program was over $30 million. And the reason for that simply is the energy security. It takes 20 times more energy, electricity, which is what DOE is all about, to produce new aluminum as compared to recycling of aluminum. And that's a basic concept. And if you look at that, we have multiple detectors, a linear X-ray tube, which is our own. So you can essentially, and there are multiple benefits. When you have a linear X-ray tube instead of a point source, the amount of power required. So instead of a 6 kilowatt X-ray tube, which is typically used in a lot of the previously commercially sold machines, our X-ray tubes is only a few hundred watts. And actually, per line, we are using less than a few watts of X-ray power, which essentially means that the tube never dies. If you're using a 50-watt tube running at 2 watts, it will never die. It has essentially an infinite lifetime. There are many, many other advantages, and which we basically systematically understood, but the limitations of the existing technology was in 2013, 2014, and solved the problems by developing our own X-ray sources and also modifying the state-of-the-art detectors. So this goes sort of, won't really go through the pictures of at every stage, but as Philip mentioned, the program started in January 2014. And at the end of the first year, ARPA-E held for all the awardees a double-blind test of aluminum alloys. And we had over 99% accuracy, which led to the funding of the second and the third year. And during 2015, we demonstrated a conveyor system with over half a ton per hour prototype built in our lab. And then we worked with, as the name OmniSource is there, and they have been pretty open about their involvement in this project. We installed in 2016 a sorter for 5 and 6 alloys operating at 100 feet per minute. And then also in 2016, we developed the old cast aluminum twitch sorting cast to 319 all the different alloys. And towards the end of 2016, we developed the algorithms for and the artificial intelligence for sorting Zorba, brass, and all the stuff. And then the photograph on the front page was for the 2 to 4 tons per hour prototype, which is essentially has gone through 6 months of testing. And we have developed the XRF sensors, which we have tested all the way up to 400 feet per minute, even though we do not have in-house conveyors running at that speed. And this year we are in commercial development of commercial sorters for various applications and different sizes. All the way, the main continuation of the ARPA-E funding, the main goal is a 10 ton per hour single machine. So some of the results, let's see. Some of the results, so these were all on the machine over at OmniSource. We have demonstrated that we can do 5 and 6 sorting with greater than 95% accuracy. And this is at speed. And we can sort 6111 from 6022 with 100% accuracy. And these are the 4 alloys, 5182 and 5754 are the automotive sheet metal alloys, which everybody's been talking about, and which was the main reason for the whole $30 million program by ARPA-E. And even though that was never really the ARPA-E funding plan, we have been able to do also the old scrap as well. Let's see. So this is the system, but it looks like 2 to 4 tons per hour. This is operating at 200 feet, 215 feet per minute belt speed. It can handle scrap sizes anywhere 3/4 inch to 4 inch, or even larger than 4 inch. This can have 4 to 8 sorting categories. Now, one of the things I will mention that all the systems Bill showed, for example, they have only one sort at the end of the belt. In our case, we can have up to 16 sorts or more if we want to, because the software and the sensors, the optical sensors and the XRF sensors capture enough information to categorize each piece into 500 different categories. And then you decide where you want to send those categories into which bin, and you assign those. And this can do twitch, aluminum, 2 tons per hour, zorba or brass much higher because of the higher weight. And we have a recipe maker. You can make your own recipes and do change or add anything. So I have a short 4-minute video. I'm going to skip through some of it, and so that we can finish. Tim is telling me to speed this up. Let's see. Hope it goes.
I do want to make sure there's time for
Okay,
questions and
all right.
answers. And you get the dubious prize of going over the most, man.
Okay.
I think your video's going to have to wait, I'm sorry.
All right. Okay.
Allow,
Let me just move it.
yeah.
All right. Most of the people have probably seen the video at the booth anyway. So, all right. Thank you.
Okay. We have 15 minutes or so at the end. We can go longer if people want to stay longer. Does anybody have a question for any of our panelists you'd like to raise? Somebody. Yes, Randy.
Carbon, is that something that you're able to sense?
Is that Dr. Nalen? The last speaker. Yeah, Nalen was the last speaker. Dr. Kumar.
You were asking about
All the alloys or all elements.
carbon.
About the light elements like carbon. Can
Um,
you accurately measure that?
With the current systems, no. The reason for that is the X-ray detector windows. Okay, not really the inherent process of X-ray fluorescence. If you want to measure carbon or any of the really light elements or gases, then you have to have windowless detectors, which means vacuum systems. And we can't really do scrap sorting in vacuum. But the answer to your question, XRF systems are available, which will do lithium and carbon and boron. They are commercially available.
But not in this.
Not in the scrap sorting.
XRF in general doesn't give you a carbon percent, an accurate percent carbon, right?
Not
Oh.
directly.
It does. If you have a vacuum WDXRF system, you can actually get carbon very accurate.
I've been in a double vacuum. It's not that fun.
Yeah, I know.
Did you have a question, Dean? No?
Yeah,
Oh, you did?
yeah, this is more back to a conventional non-ferrous plant. Most people run, everybody I see runs a regular strength magnet to remove the saleable ferrous. Some in the 1,500 to 2,500 Gauss range. And this is probably better answered by you, because you work with magnetics. Have you experimented around with using a high Gauss magnet, something in 10 to 12,000 Gauss range, to remove the lightly magnetic waste? You know, the ferritic dirt, the fuzzy ferrous, rust dust, magnetic fuzz, things like that.
The answer is yes. So,
You have.
yes, we have.
Okay.
So you can do that with a magnet. Of course, the care to be taken is entrainment of valuables in that otherwise non-value stream by the magnetic traffic. So that's the care that has to be taken. But it's called debulking. There's ways to do it with air, which for example, the Lead Corporation can tell you a lot about, and we've done it with magnets as some of our other magnetic suppliers have done. And that is a much higher Gauss, an 8,000 or higher Gauss range. gals and gradient, so be careful with just getting 8,000 gals, but that's the gals.
Okay, thank you.
Other questions having to do with our panels? Oh, you're not going to let them off that line, are you? No one must have a difficult question.
All right,
Okay, Randy, you're back up.
the last speaker, I'm sorry, I didn't.
That's Mr. Dr. Moore.
Okay. The multiple sorting at the end of the sensing.
Yes.
You said you could do up to like 16. I saw the bins. How was it choosing which bin? Was it single particle and it was pushed
That's
off to the
correct.
side?
Yeah.
Or?
So we have two ways of pushing the, so the computer keeps track of where each particle or each piece is. And then it can, at the right moment, where the piece reaches a particular, the desired bin, we have two methods to push that into the bins. And one is the air jets, which in this case are different than the typical air jets used. We had to develop our own air jets because they're going 90 degrees to the flow of the material. And the second one, for one of the applications we have been looking at, is very heavy brass pieces, which are almost a kilogram. And the air jets do not push those. So we have electromechanical plungers to push those pretty fast plungers.
So it's assuming the pieces are coming single file down the belt.
That is correct.
Okay. All right.
Yes.
Would you, for Mr. Close,
Yes.
would you recommend running the extract and CombiSense online with your other existing non-ferrous systems, or would you have them totally separate batch run systems?
All right. We would recommend running them offline. We've had some experience where we've connected them to the large eddy current plants, which had a high throughput. But the situation was basically XRT had this much capacity, and in real time we were using this much of it. Okay? So for every hour we were running, we were leaving that much on the table. Far better to have it offline, make a stockpile, run it using the full capacity, shorter hours for that source material, creating available opportunity for other source material and other processing activity.
Yes, please. This is for Dr. Kumar. With neural nets and the computer keeping track of all that, how much computing power do you need to run one of these things?
Well, the first machine we built, we did not know how much computing power we were going to need. So we had 6 computers on it, six core computers. Our current machine right now uses a single 8-core processor. Now, when we develop the algorithm and the neural networks, that is, of course, done on cloud because we need extreme computing power. When the training process, 12 hours of enormous Amazon's cloud server.
Some more questions? I'm very impressed with the dedication of this crowd that came out on a fine day after the trade show had closed. You could be enjoying oysters on a half shell or something, and you're here with us. Thank you. If there's no more questions, let's give our panelists a hand and thank them for their time.
Close.
Yes.
Would you recommend running the extract and CombiSense online with your other existing non-ferrous systems, or would you have them totally separate batch run systems?
All right. We would recommend running them offline. We've had some experience where we've connected them to the large eddy current plants, which had a high throughput. But the situation was basically XRT had this much capacity, and in real time we were using this much of it. Okay? So for every hour we were running, we were leaving that much on the table. Far better to have it offline, make a stockpile, run it using the full capacity, shorter hours for that source material, creating available opportunity for other source material and other processing activity.
Yes, please. This is for Dr. Kumar. With the neural nets and the computer keeping track of all that, how much computing power do you need to run one of these things?
Well, the first machine we built, we did not know how much computing power we were going to need. So we had 6 computers on it, six-core computers. Our current machine right now uses a single 8-core processor. Now, when we develop the algorithm and the neural networks, that is, of course, done on cloud because we need extreme computing power. When the training process, 12 hours of enormous Amazon's cloud server.
Some more questions? I'm very impressed with the dedication of this crowd that came out on a fine day after the trade show had closed. You could be enjoying oysters on a half shell or something and you're here with us. If there's no more questions, let's give our panelists a hand and thank them for their time.
Thank you.